Welcome to the Polaris Laser Labs at the Helmholtz Institute in Jena. Here I'm standing in the control room from which the laser is controlled during the experiments and during the alignment procedure. Polaris is the most powerful fully diode-pumped laser system in the world, which we use for particle acceleration experiments here in Jena. We also use it for laser development, since this technology is also relevant for laser systems at GSI in Darmstadt, at HZDR in Dresden, and also at DESY in Hamburg. However, as I said, we also use it for an extensive research program on laser-driven particle acceleration, also together with the Yeti system. The experiments which we are carrying out with Polaris are actually controlled from this room because all the other laboratories and also the target area are not accessible during the experiments. However, today we have the chance to show you a little bit of the details of Polaris, and for this we can actually go into one of these laser laboratories.
These labs are inaccessible when the laser is running. Here we are in the final amplifier of the Polaris laser system, which is obviously off. Polaris is a double CPA system based on the Nobel Prize-winning chirp pulse amplification. This produces pulses of extreme laser contrast, which is necessary for controlled experiments. In the last amplifier, which you can see here, 120 laser diode stacks, each having a power of 2.5 kilowatts, pump the active medium in the center. This boosts the pulse energy in excess of 50 joules finally. After that, the pulses have to be recompressed, which is done in the lab next door, to their initial pulse duration of 100 femtoseconds. With this, they reach the highest peak powers and can be delivered to the experimental target areas.
So here we are in the target area where we carry out experiments with the Polaris pulses, for example, on laser-driven ion acceleration. This is the target vacuum chamber in which the Polaris pulses of about 15 centimeter diameter are focused to micron-sized spots, reaching peak intensities of up to 10 to the power of 21 watt per square centimeter to accelerate particles from micro and nanometer thin targets. Using a synchronized ultra-short probe pulse, which is generated here, we have been able to take snapshots of the ionization processes and the plasma formation driven by the Polaris pulses, and take a closer look into the interaction processes, which gives us unprecedented insight into the acceleration physics.